OK，我们开始上课。最近课上的非常的频繁，大家都很辛苦。我了解到有的同学昨天半夜还在证明微信，所以有的同学还是非常的想学好这个课，很热爱这个课。OK， 我们继续今天的课。So, last time we discussed about the correlation function. So if you insert fields and measure the eigenvalue, we find the correlation function. We also discussed the propagators, which looks a little more physical. Among those, we in particular discussed the different types, the 4 different types. Right? We have retarded, and the different types of propagators are beautifully classified by different contours. We spend a lot of time to explain why they're following does the job. Okay? So last we also mentioned the Lakers theorem, and that you to prove it yourself. And many students indeed try very hard to prove this theorem. That's great. So the problem is we are going to continue today the interaction theory today, and all those is only about the free theory. All those only about free. And what about the interaction? Free theory is beautiful, but it's a little trivial. In free theory, you can see the excitation of particles about how the energy differs and many stuff. That's beautiful because you can get a precise result, accurate result. But this is a little trivial in the sense there's no interaction. Okay? There's no interaction. Everything's free. So if you consider 2 different particle states, they don't touch each other. Never. Okay? It's just because there's no interaction. In the Hilbert space, if you prepare particle state, you can prepare many particle states, but those particle states will never touch. Because everything's free. Then what about the interaction? Or interacting theory. Then the first question you could ask is, what do we mean by interacting theory? First question. You get what? How can we define the interacting theory? This should be there should be a very simple answer, right? How do you define the interacting theory? That you already saw previously when we talk about the free theory, the equation of motion looks like this, right? Right? So equation of motion level for free theory is linear to phi. What do you mean by linear? Linear is this. It's only a one movement of phi, not 2 phi, 3 phi. Put together, okay? Linear in phi. Then interacting theory essentially means at the equation of motion level it will be nonlinear. Okay? Now, of course, here phi is only represent some fields. Think about different type of fields. The point is, whenever the equation of motion is nonlinear in phi, there's an interaction. Okay? Then, if you like, you can go back to the one. Then you ask, what about the Lagrangian? Okay? Right? You can justify yourself because Lagrangian is go beyond the quadratic order. Previously, our Lagrangian is many phi squared, or partial phi squared. Okay? All are the quadratic. Okay? Quadratic R. So, okay? Then the conclusion will be if your Lagrangian go beyond the quadratic order. For example, you have cubic, sense. If you quartic, sets, then this will be interacting theory. Okay? For example, we can consider some terms, as we mentioned, some terms like cubic coupling. You can also consider about some terms like quartic coupling. All those are interacting theories. Okay? Defining interacting theory seems very obvious. Now, the true question is how to calculate these theories. To calculate these theories. That's the main task of today's lecture. We will basically go step by step. Okay. But first, First, let me mention other things. For interacting theory, solutions to equation of motion. Because as we discussed, we want to quantize it. Following Heisenberg the approach, you can first find the equation of motion if you could, then promote to operators, then maybe the job is done. Now, the point is here is the solution to equation of motion for interacting theory. For interacting theory, it's not possible. As you can check yourself. Because this is a highly non-trivial PDE equation. You should find the exact solution. It's very, very hard. Very, very. Then what we can do? So maybe we should step back. The strategy is not going to quantize everything, systematically. Rather, we step back to ask ourselves whether we can calculate something. Okay, we already learned the main object, one of the main objects to compute is kind of correlation functions or propagators. Okay, or propagators. So this propagator when this df it evolves some time ordering operation. Okay, So maybe the full question to ask is whether we can compute something like this. Okay, something like this for the interacting theory. For the interacting theory. Now, since the theory is interacting, you can expect the vacuum will be different from the free theory, right? Then we can change to another notation. Usually, you can denote for the interacting theory the vacuum in another way. It's just the vacuum. It's not a big deal. Different label. Okay. Maybe we should first ask how to compute that kind of thing, like a time ordered correlation function. Some others, if you want, if you can try. For the interacting theory, that will be the first. Okay. Yeah, this is our strategy. This is our strategy. So, from the calculation of such object for interacting series, we're going to see we can derive something called the Feynman rules. Okay. But you have different approaches to achieve the Feynman rules. Once you obtain all these Feynman rules, then you can forget about the derivation. To follow the rules. Then whenever I hand you a problem to compute something like this, you can just follow the rules and you write down the results. Okay. So that's the idea. So eventually, to compute this one, we're going to arrive at some those. So here we employ an approach called Lagrangian approach or Schwinger-Dyson. It's a beautiful approach, but there are many other approaches. For example, you can try to using Hamiltonian or path integral. There are three different approaches to derive the Feynman rules, but maybe due to the time, we don't have enough time to cover all those. Maybe we'll just cover Schwinger-Dyson, and a few weeks later, we're going to discuss the Feynman, the path integral approach. Then we'll also talk about this one, how to use path integral to derive the Feynman rules. If you like, you can derive yourself, or in the Hamiltonian, for example. That's the third approach. Okay. Before this, then you might curious about why. What is the physics, right? Why you are trying to jump into to compute such kind of object? This is not something we just want to challenge ourselves. This is really due to a physical motivation. Okay? With the motivation. Okay. The motivation is really coming from the experiment. Okay. Experiment. So why we care about for the interactive theory to compute something like this? The motivation is really come from the experiment. So see, for example, there are many big experiments like RCC or some other colliders. All these experiments are designed, constructed to do the scattering of particles. Okay. As I mentioned earlier, for free theory, there's no non-trivial scattering. Okay, all the states just pass through because there's no interaction. Okay. In the fundamental level, there's no interaction, so they cannot touch. And but for interacting theory, things are quite different. Okay? So they can scatter. Okay? Scatter means these two particles can collide and then become something new. Okay? So that's the scattering. This is the big motivation why we care about it. correlation function, scattering, or sometimes we simply use this is a matrix. So what is this? How to define this one? As I said, it's very, very simple. Just consider there are some experiments. So the construction of S matrix. S means scattering, okay? Obviously. S matrix is motivated by real experiments. See, collider experiment. Okay. So what is collider experiment? It's actually very simple. You just think about if this is your time direction, okay? This is my time direction. Then you just think about you prepare from very far distance away. You prepared some state, okay? Prepare some state. You design some state. Then you let the state evolve, okay? Or aim them to just collide, okay? That's the easy experiment. You actually learned in your quantum mechanics, right? A little bit about scattering, okay? You just let two particles colliding. And then when they collide, okay, they produce some new particles, okay? The whole process is highly non-trivial, but to make the story easier, you can reasonably put some assumptions. Okay, the assumption is when these two initial states are very far distance-wise in space. Okay, when they're very far from each other, you can think about there's no the interaction between them is nearly zero. Okay, you can think about those states are free state. These are free state. And then they evolve, right? They evolve, they closer to each other, and then they experience some time, okay? They experience some time. This is my time direction. Think about it. Then I can idealize this story to such a sample model, which is then they produce some new state, right? Produce some new state. I can idealize this process into a sample model. Say, initially those states are free, okay, because they are very far from each other, okay. Then they come into some time window, okay, some time window. Between this time window, there's interaction, okay. Okay, this is idealized model for loopholes. And then after this time window, it becomes some new particle states, okay. That's very reasonable, right? That's what we do the collider experiment. Then after this time window, we also think the output states are also free states, okay? Because why? Because when after the collision, then they just scatter out. The output, okay, they will just come and then becomes also very distant far away from each other. I can think about then eventually they can become some free state. So here is free, here is also free, okay? And the intermediate is interaction. Okay? Then you can imagine if I allow myself to let this interaction window to cover long enough time, okay? Then it will be okay, right? I just design this whole scattering process to let this intermediate window very, very long in the time direction. Then it should be okay. This should be a good model or ideal model to model my scattering experiment. It's very simple, right? Now we're physicists. We want to write everything in terms of formulas, okay? How to do this? It's not very difficult, very simple. But for that, let me write it. It's the important So at t equals to plus infinity and minus infinity, one can ignore the interaction. Therefore, the in state and out state, we call it, in this case, we call in state, and also out state can be described by free particle states. We are already very familiar about the free particle state, right? Because free particle state was covered by free theory, okay? Initially. Or in this case, we call it asymptotic state. Asymptotic means in the post-quantum process, we are asymptotic states, okay? Now, since these are free states, you can just write it down very easily because we already discussed a lot in after the quantization of my free fields. Then look into the hyperspace, I can find some free state, whatever free state was there. Okay. For example, I have k particle states for my initial state, and for my final state, I can have n particle state. Example. Okay. Then once you have the initial in state and out state, then what about the interaction region, right? And what about the region? Okay. For these two, you know what are the state. Then what about this region? Then you can write this way because we already know this state has no time dependence. Okay. Why? Because we quantize the free field, say, following the Heisenberg picture. The Heisenberg picture, there's no time dependence. The time dependence was included in the operator. Then we can easily consider the amplitude. One can consider the whole process, which is the initial state evolve, okay? Evolve following some, for example, some operator or some matrix, okay? That matrix will go from the minus infinite time to plus infinite time, okay? And then overlap with the final state. You see? This is the formula to cover the whole process, okay? Okay. Actually, this formula is a little more precise than this ideal model, okay? This formula is just enough about the is you can write down some evolution matrix to cover it as long as you want for the time evolution region, okay? I just only need to assume really the infinite past, the state is free, and the infinite future, the state is free. That's it. It's only the assumption I need. Okay. Then I can write down this one. This is will be we call the amplitude, of course. If it's not precise amplitude, this is just an overlap for the evolution process. Okay. So emphasize this is the Heisenberg picture. Heisenberg picture. If you don't like it, then maybe if you insist that I like the Schwinger picture, then what would be the Schwinger picture? To compute the same thing. This is more straightforward, then, right? Then in the Schwinger picture is nothing but this one. Okay, right? But in the Schwinger picture, the payment will be the state it carries a highly non-trivial time evolution due to your interacting Hamiltonian. Okay, because the state always follows the Hamiltonian to evolve. And then for the interaction theory, this Hamiltonian will be highly non-trivial, and it will be a lot of us. Okay, in this time dependence in the state. This is not very convenient. Usually we take this picture as we emphasize in the beginning. Okay. Now, this actually put the this put the definition actually of my so-called S matrix. We're going to introduce the notion of S matrix. So what is that? So S matrix is defined in this way. Okay, it's defined in this way. This defines my S matrix element. This. Okay. Look, I put I and F as index of my S matrix. Okay. Okay. Understand it, right? This means what? This means different S matrix elements corresponding to different in and output state. Okay. Okay. And the S matrix element measures the transition between different in state to different out state. Okay. That's what the S matrix does. This defines the conceptually it's very easy, right? I mean, maybe the calculation will be challenging, but at this moment, the concept of this S matrix is pretty simple. Okay. Very simple. Now, think about some scattering process. As said, if the series is free, then this part will be trivial. Okay. Okay. If the series is free, this part will be trivial. What do I mean by trivial? Trivial means whatever you get as input, you get as output. Okay. That means trivial. Okay. You can think about it that way. Then it means what? It means this S matrix element is identity. Okay. The identity transform nothing. Okay. So whatever you give me, I just output that. Same thing. So in that sense, it's trivial. Now, because of that, so you can think about it, if the interaction is weak. Weak means the interaction is the interaction is weak means there's a little bit more interaction, okay, above free series, okay. You can think about the scattering, non-trivial scattering here is small, okay, or the probability is small, and then in that case, I can split my entire S matrix into the identity plus something, okay? Something, as I said, in free case it will be equal to identity, okay? Okay? Here I write everything in terms of matrix, okay? In terms of matrix, this is the identity matrix. S will be a big matrix, okay? Will be a big matrix. The S can be split into identity plus something. T is also a matrix. Plus IT. So we call it the T is the matrix, and the T captures the interaction. It's just a definition. The T matrix captures the interaction, as you can see. When T is non-trivial, the interaction will be non-trivial. Okay. And in free series, T will be 0. So this is some notion. So one more thing is, to think carefully about the in state and the out state, or input and output. Then you realize that, as we learned in the middle school, okay, whatever non-trivial scattering it is, the energy momentum has to be conserved. Okay, okay, because the energy momentum capture the global property is from following the symmetry. Okay, the energy and the momentum has to be always conserved. Okay, because I don't care these details of this the medium. This particle collided with that particle becomes the third particle, whatever. I don't care. The point is due to the conservation, the energy momentum has to be conserved. So this is a physical collider experiments. Yeah. So because of that, because of the conservation of energy momentum, we can further write it's a T matrix. Okay. Now to be explicit, let me write this matrix element. This T matrix, I can further extract some factors. For example, these 2 pi to the 4th. The point is, we want to extract, we want to separate out some delta function, okay? Because of conservation. Now we're talking about a conservation in the momentum space, okay? Then we can separate out the delta function. The space is 4 dimensions with the 4 delta function. Okay, this is just a definition. Again, it's not a big deal. So we know what we're doing. Okay, there are some physical reasons allow me to do this. Okay, so turns out to be this M is a little better definition. Okay, so this M is really called the scattering amplitude. Okay, we call this M scattering amplitude, or some kind of amplitude for short. Okay, so these are just different notions. Because this is the first time we introduced the S matrix or scattering experiment. Okay, this is important because it justifies the value of all our theoretical work. Why we do a lot of these calculations, and seems a very, very difficult task to calculate something because there is a big value. The motivation is we can use that calculation to fit or to compare with the experiment. Okay. Now maybe if you're familiar, a little bit familiar about the experiment, then you keep ask, is this scattering amplitude the true physical observable? Can we see this scattering amplitude just from an area to see? Okay. Can we see that? Can we really measure that directly? No? Then what is the observer?
But we can't detect its phase.
Good. So what is the true observer? We can directly observe from a LiDAR experiment. You should know, right? Because in quantum mechanics, you learn some scattering. What is that? There's a name for that. So the true observed quantity is cross section. Okay, it's cross section. Okay, but there is a way to bridge how we connect the cross section with this quantity. Okay? There's a beautiful theory there. Okay, not a big deal. But as a theory, we will stop by this. Okay, we're not going to continue to discuss this cross section or differential cross section. To really connect to the experiment. Okay, we'll stop here, and just to give a few remarks. So number one. Since clearly this S matrix come from this evolution, okay? See, this is his definition. This is the definition, origin of this S matrix. It come from here, okay? What is this? This is the evolution matrix from some initial state or from some time to another time. You see? As we learned in quantum mechanics, whatever evolution matrix has to be unitary, okay? Clear? S must be unitary, so that's the first property. So S is unitary. Some people from there cannot see it. Let me first finish the writing and then upload the file. So S has to be unitary. Second, as we emphasize the in and the out state are free, okay, are free. They are free on shell state. On shell state means they satisfy the on shell condition, okay, the physical state, but not some virtual state, you know, in Fock space. Okay. This. Now, last and the most important thing, maybe let me put it here. Here is the last and the important step is as a motivation. This S matrix directly connected to this time ordered correlator. Okay? So that's the reason why we introduce S matrix as a motivation. So previously we talked about last time we talked about the time ordered correlators. Okay. Now this time we introduced a new concept which is the S matrix. But point is these two are directly connected. Okay. Means if we know how to compute the time ordered correlators, we can use that result to directly compute the S matrix. Okay. So that's the connection. So this connection between S matrix and time ordered correlate is given by a beautiful formula. A beautiful LSD formula. Again, I'm not going to prove this formula. We're going to just tell you what the formula is, and you should prove it yourself. We're going to assume this formula and directly go to the next step, how to calculate time ordered correlator for interacting theory. And then through that, by that formula, we just use the results, calculate the results. So LSD, that's three people. The name for three people. Okay, the three people is Feynman, Demanzik, and Zimmerman. So what is the formula is? Roughly speaking, the formula is saying that the S matrix element, think about it a little bit. If there is a connection, what could be the connection? Because S matrix is really defined in the, if I and F state is written in this way, you can see that the S matrix is defined in the momentum space. See? Right? So S matrix is defined in the momentum space because it's measured the transition between in and out state. Those in and out state are in the momentum space because they're the free particles. Okay? So S matrix is defined in momentum space. However, correlators are so far all defined in this coordinate space, okay, or position space. See? So if there is a connection, the connection could be some relation like Fourier transformation. Okay. So if I do Fourier transformation for time ordered correlator in position space carefully with some factors, then maybe I can get the S matrix element. That is what the LLC formula tells. Okay. So write explicitly. It's a bit long formula. Hopefully we can maybe also do something like this. do this. Good. That's it. Okay. That's it. That's it. It's a little bit scary formula, but you shouldn't be scared. Okay, because it's the fact the relation is simple. Let me explain. Okay, once you understand it, it's okay. As said, it's roughly speaking, just as said, the S matrix element is the time ordered endpoint function. Time ordered endpoint function. You do Fourier transformation. Okay, why? Because you see there is a Fourier transformation kernel. Okay, the e to the minus I p1 x1. That's the Fourier transformation designed for x1. Okay, and there is a p n x n. There's a dot 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 dot. Of course, there are many cover all the endpoints. Okay, then there is a p n x n. This is for Fourier transform about this x n. Okay, to p n. Okay. So roughly speaking, the Fourier transformation, but more than that, as you can see, there are some factors. There are some additional factors inserted before you do the Fourier transformation. Those factors will be factors. Those factors. Okay. And also there are dot dot dot. Dot 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 means there are n copies like this bracket. Okay. In the dot dot dot. And there's a detailed important thing, which is here there's an endpoint, but what about this left? So left, to be precise, this in state will be the P1, maybe P1 to PK, okay? And the F state will be the PK to PN. The F state will be the from PN to PN. Okay, this is the in state and this is the out state. The point is, how can we see from right hand side how to distinguish the in state and out state? Right? We know in state and out state are different. You cannot mix them each other because in is in, out is out. Okay. So from right hand side, how can we distinguish those? Where is in and where is out? The point is, for in state, there's a minus sign. Okay. For all the in state, there's a minus sign in front here, in front of IPX. Okay. But for out state, there's a plus. Okay. So you have m copies here, but only for the in state. For the in state you put all the minus sign. For the out state you put all the plus. Okay? Then you can distinguish. How to prove this one? Yeah, I leave you to do your. It's an exercise to prove it. So, yeah, this is roughly the Fourier transformation, and once you understand how to prove it, the quick comment now here is this factor are essentially designed to cancel some factor appear in the correlation function but does not appear in the amplitude or in the S matrix. Okay, in the S matrix. Okay. So do you have any questions or how to define S matrix, and what is the relation, what is the precise relation between S matrix and the time ordered correlation function. Yeah, it's not super difficult, by the way. It's just a long formula. It doesn't mean it's difficult, okay? Because this box, I write this box a little bit scary because this is just an operator acting on this x1 to xn. It's the position space. Translate, if you think about it in quantum space, this is just a p square m square. Okay? It's just a p square m square. This p square m square will be cancelled. Will cancel some correlators in the momentum space. Okay, because as we already know a little bit in free theory, you can Fourier transform your time ordered correlation function to momentum space. Okay, you get some p square minus m square plus I epsilon. Okay, as the denominator. Okay, then you can imagine there are endpoints. Okay, as we learned from Wick's theorem, then there could be many such kind of structure. 1 over p square minus m square. Okay, and the sum of the 1 over p square minus m square will be cancelled essentially by those factors. Okay, then there are something left over. Okay, that left over thing is essentially the S matrix. Okay, so there is a precise connection between S matrix and the momentum space correlator. That's the short message. Okay, the short message. We are going to compute for some examples by using this formula in a very concrete way. Okay, even though this formula at this moment, as a general form, it looks complicated, but in practice, once you need to compute for a particular diagram, it's very easy. Okay, very easy. We're going to do it. So, do you have any questions before I continue to develop my Feynman rules to compute the time ordered correlators?
然后这个 m 是裸量还是物理的质量
M is mass.
它是那个拉朗量里，它是裸量还是物理的那个质量？啊，它说静质量、动质量，有没有同等化后的这个 m？
No, at this moment we don't talk about any renormalization. It's just the mass appeared. It's just the mass appeared in the Lagrangian. Okay. Just the mass appeared in. Any other question? Okay, so let me continue. So derive Feynman rules. Yeah. So as I said, I choose to employ Schwinger-Dyson approach. Maybe slightly different to some traditional textbook. Okay, because some traditional textbook usually prefer to introduce or to derive Feynman rules by using this Hamiltonian. Okay? But here we're going to use this Schwinger-Dyson. Okay, I like this because Schwinger-Dyson looks more non-perturbative. Okay, there's some equations really non-perturbative. It's intrinsically non-perturbative. You will see what I mean because we're going to write down everything very soon. And yeah, you can judge yourself afterwards, after you understood all the different approaches to arrive at the Feynman rules. So Schwinger-Dyson. The first question to arrive there, the first question we have to address now the Schwinger-Dyson approach of Feynman rules. Okay? The first question is we all talk about the quantization. So this is for interacting theory. We will have to quantize it. We want to quantize it. Then you ask what would be the quantization condition. And for free field, we learned that days ago, we learned that the quantization goes like this. Right? These are given by the so-called equal time correlators. For example, for phi commutator at equal time, we know this commutation relation is 0. Okay? And for phi pi, we know it's non-zero. Also equal time. We know this is non-zero, and this is some phi, a delta function. Since this is a commutation relation, as we learned in quantum mechanics, we all by now we all use the natural units, which means I set h bar equals to 1. If you want, you can recover your h bar. H bar is here. Okay. So this is the quantization condition we use for free theory. Now you ask yourself, since the quantization condition is extremely important, right? Without knowing it, how can I quantize my theory? Okay. Now the question is, for interaction theory, what would be the correct quantization condition? Should we use the same commutator or commutation relations? What is your guess? You can guess. What do you think? For interacting theory, now my theory is not free anymore. Which kind of quantization condition you expect to be true? Any guess? What do you think? The point is the quantization condition is not something we can derive for some more fundamental principle. Okay? So about that, quantization conditions themselves look very, very fundamental. Okay? Okay? It's not something you can derive. That's the point. Okay? It's not something you can derive. It themselves looks very, very fundamental. So, in that sense, quantization condition is something you impose, okay, and then you justify whether those quantization conditions are proper or not. In quantum mechanics, we learn a lot. We believe that we found the canonical quantization conditions; they are reliable. Okay? In field theory, the same. In free theory, we checked many things, right? After using this quantization condition, we checked a lot of things. Seems a proper quantization condition. Now it seems there's no reason we should change those conditions, even for interacting theory. Okay? So let's impose the same condition. See what will happen. I said it's not some result we can derive from some other principles. Okay? So let's impose the same quantization condition even for interacting theory. So these are fundamental conditions. Assume that to be still true. Interacting system. let's use it. We're going to use this to compute this one we want. And for the first thing, we're going to step by step, okay? In order to compute a general question, usually we have to prepare. We have to prepare. We have to go step by step. We're going to use some key relations. First of all, we have to be able to first derive those key relations. Using these key relations, we can develop a systematic approach. So the first key relation we're going to prove is this one. First one. First, show the following relation. Yeah, first we're going to prove this one first. But maybe you can first try a few minutes yourself. Because this relation looks a little similar to what we proved last time. To check whether the time order correlates to a Green's function. Okay? A little similar. You can first try yourself. Try to prove this one.
那东西不是对啊，我出来也是 A 吗？就直接干成点单。
You can discuss with your neighborhood
它左右不是零。
how to prove it.
这里差还是我猜是这样，我猜这样。因为你这个页面上不在右边，但是它就一直在那页上，我它一直在左边。
Try to discuss with your neighborhood if you have some ideas or if you finish, or just exchange ideas. Okay, let's see it together, this problem. So the whole thing is trying to clarify how to pass through this time order using this box, right? See, it's clearly then it's not trivial. Okay, it's not just trivially shift inside. Okay, it's not trivial. Then how to do this? How to calculate this? This is the process. Well, we can go step by step. Not a big deal. So whenever there's a problem, at least we should try do the calculation straightforward or brute force. Okay, step by step. So this box is about twice the derivative. Okay, twice the derivative. As we emphasized last time, the time ordering is only about to change the time. Okay, to change the time. Incorporating some theta function, for example, okay? It's nothing to do with other x or y or z, okay? It's only about the time. So the real thing matters is about the time derivative. Okay? The time derivative is not commutative with this t, okay? So time derivative is important. So and then the box included the twice time derivative, okay? Partial t squared. So if you want to know how the partial t squared act on this time order, let's do it one by one. Let's do the time derivative first. One time derivative first. Okay, so proof. So let's first do the partial t. See how the partial t acts on this time order. So what is this? This by definition will be just I can write it as a theta function. Okay?
不是，这边黑板读稿。
I will. Okay. This is by definition. This is by definition. See, this is time order. I can write it as a theta function. Now, what is this? You think about it. What is this? So there are some, because as emphasized, the box is always acts on x, not x prime. Okay, the box is box x. Okay, the box means box x. Okay. So there are potentially a time dependent here. Okay. Okay. Here is in this operator. There are also a time dependent here. Look. The same thing happens here and also here, right? You take the partial t time derivative. You should care about all those possible time dependent. Okay, and do it actually on one side and work it out. So then you realize that this is nothing but two pieces. The first piece is I only act the time derivative on this phi and on this phi. Then at least there will be two terms. Okay. One is from here, and from here. I don't touch the, I don't act the partial t to this theta, and let the theta near here. Then still there is a nice theta function structure I can write the two terms, combine them together, then will be again time ordered, but the time ordered with the partial t inside f of phi x, and then phi x prime. Okay? These are the two terms, okay? See? These are the two terms only with this partial t acting on this part, okay? Without touch is 2 theta. But there are two more terms, you see? Two more terms, the four terms together, okay? Two more terms with partial t acting on this theta, okay? What is those? This function, when you take a derivative, you get the third function, correct? So the left over two terms are the third functions. And also remember that there is a sign flip here, because the partial t always act on t, okay? When it acts on t, you get a delta here, but you get a minus delta here, okay? Minus sign. So for that reason, the leftover two terms, I can write the third function, extract the third function in front, then there's a commutator left over. Okay? There's a commutator left over because there's a minus sign. So there's a minus sign. See? The commutator is given basically by this minus this. Okay? And there's a third function in front. So these are the results. Now you realize that what is this? We know the result for these commutators, right? We know the result for these commutators. Look, right? Why? Because there's their function in front enforce this commutator becomes the equal time commutator. Look, right? Right? Otherwise it's trivial. Now for equal time correlator, this is the quantization condition. And we use, as said, we use the quantization condition here. What is that? 0, okay? This is 0. So you can chiefly forget about the second term. Only this term. Okay? So this is the first time derivative act on this time order correlator function. Now just do it, repeat this procedure once again, and get the result. Okay? Do it again, because we have one more partial t. Let's act on partial t for this one. Okay. Then we get the result. See? Then you actually you don't need to do more things, right? This is like some you don't need to do one more thing because every thing there, you just change, you properly change the object acts on. So take one more step. Take one more partial t. Of course, one more partial t means act on this object. Then what you get is partial t squared. This will be equal to what? Because for this one, we already know as a result, whenever you act once a partial t, the first term will be you just shift this partial t inside, okay? Okay, whatever inside is, okay? Just shift it to inside. And then it also produce some extra terms. The extra terms will be controlled by a direct function with a commutator. With the commutator is basically the commutator with whatever originally you have these two terms. Okay, that's the rule. You see, this is the rule. This calculation does not really care what is here. Okay, okay. You can change this to some other. You also get this. This looks like a rule, an acting rule. Okay. Now, knowing that one, now if I want to act a partial t once again on this object, I just change the original phi with the partial t phi. That's it. I employ the same rule. Okay. See? So knowing that, I immediately write down the result. The first term will be the partial t squared prime. This will be my first term, okay? And my second term will be, again, controlled by delta. And the following term will be the commutator between the partial t this time, partial t phi and phi x prime. It's not the same commutator as before, but a new commutator, okay? I just following the rule, replace the previous phi by this new partial t phi. See, using the same rule, okay? This is the result. Now the interesting thing happens, because this commutator is non-trivial, okay, compared with before. Previously, phi commutator is 0, following the commutation relation. Now this new commutator, we produce something non-trivial. You see, this is the pi phi commutator. This is the pi phi commutator. Now I use the second commutation relation or quantization condition. Here, I will get what? I will get this term. This term is precisely. This term is precisely the minus I h bar cos third function. Okay. This is the third function. Because as said, this contributed a three-dimensional third function combined with this third, like a fourth third function. So what? So what? So I proved that one, okay? I finished the proof. Finish the proof. Now you might ask, you are not only talk about the partial t, but the original equation is the box, okay? But as that, apart from partial t, all other is trivial, okay? All other is like partial x, partial y, partial z. But all those is commuted with time ordering. This time ordering does not touch space coordinate, okay? You can shift whatever you want. Okay? So finish the proof. Maybe you still wonder about what's the meaning of this equation. This equation seems new. I'm not sure I understand it. Then you should check it yourself. See whether this equation is really meaningful. You can check. Okay. Let's do some check. Check what? Let's say for free theory, what that equation tells. I here use all the vacuum to denote that this will be interacting theory. You see? I don't use the free theory vacuum. You see, meaning this is interacting. For interacting theory, this is generally true. But now what happens for free theory? What happens for free theory? For free theory, we know the box plus m squared acting on phi is what? This is 0, okay? 0 from equation of motion. Okay? This is 0. Now, it means for free theory, this is trivial. Okay? Because box plus m squared act on phi is 0. You impose equation of motion. Okay? Then what do you get? You get that equation given by or simplified to box plus m squared acting on something equals to delta only, okay? Right hand side. And what is that equation? This is a perfectly correct equation, right? Because this is the grand function equation for the Feynman propagator. So you check yourself in free theory, this is perfectly correct. This is nothing but this equation, okay? Which we already proved, or I leave it to prove to you last time, okay? So this is the green function equation for Feynman propagator in free theory. So today's course, we're going to use this df repeatedly many times. So let me emphasize, whenever I write df, I always mean free theory or free propagator. Free propagator, Feynman. Okay. We denote the df always means the free Feynman propagator. So in this case, we check. In free case, this is indeed true. And again, we need to do some preparation for the later calculation. So quite often, in quantum field theory, because many symbols looks very complicated. Okay, so we're going to use a short notation. Okay, to simplify, to shorten my long formula onto a simple. So we're going to use some short notations. For example, from now on, we're going to simplify some notation. This kind of notation. This kind of excitation value for the interacting theory vacuum. We're going to use a shorthand. Okay, shorthand. We're going to use the we're going to use a simple bracket to denote both interacting excitation value, interacting theory vacuum, excitation value, and also the time order. We don't want to use it. We don't want to write this time order and this omega state too many times. So short notation. We're going to use this simple bracket, just a bracket, to denote both the vacuum and also the time order. From now on. And with this short notation, we're going to generalize this equation. Let me call this equation is my star equation. Okay? We want to generalize the star equation. And then also we want to generalize star to what? To endpoints. Endpoints. That's only 2 points, right? You see, little trivial. It's just 2-point function. Our goal is to handle endpoint function. Okay. So what is the endpoint function version of that one generalization? That's also very interesting exercise. Right? You should challenge yourself how to generalize it to endpoints. Maybe you can first do 3 points and then you observe some general structure. You just promote to the endpoints. Okay. So what is the endpoint function relation for that one? The endpoint function relation for that one is actually simple. It's just about how act the box to some time order. Now I simplify the notation. Just use the bracket. You should know the meaning of this bracket. It actually carry this time order and direct reaction. So again, the first term is I shift the box inside. And there are crucially important second term. Previously, my second term in the case of two-point function is just a I bar delta. Okay, it's just a delta function. Now for endpoints, it's no more true. It's a simple delta function, but it's a delta function with some following. Multiply some terms. Okay, it's a delta function multiplied with n-1 point functions. Let me first write and then explain that. This is what happens. Again, it's a little scary. It's not a big deal. You should get used to some kind of long formulas, right? The point is you have to understand the meaning. Once you understand the meaning, it's okay. Now let me explain. This means what? This means in general case there is a delta function in front, fine. But the point is the leftover thing you have to multiply with some correlation functions. That correlation function precisely without this xj insertion here. Okay, you can check yourself. Okay, and of course without x. Okay, so compare with this original insertion or original n plus 1 point functions. It's 2 points lower. Okay, 2 points lower because x is gone, xj is gone. Okay, that's what happened for this following correlation functions which multiply with this third function. You can check yourself. It's perfectly consistent with this 2-point case. Right? So in this case, this is 2 points. So original function is 2 points. So when you have 2 points, then 2 points lower is 0 points. Okay, 0 points means there's nothing. It's not a correlation function. It's a trivial, right? Trivial number. So you only have third function. Reasonable, right? Consistent. Now you can view this as a fact because it's a straightforward generalization. Yeah, I'm not going to prove it. You should do it. Right? I'm going to use it. I'm going to use it. Now one more step. That is the first step. Okay. Now one more step. So far we didn't specify. We actually derived those equations. We are here for general interaction theory, right? For general interactions. Now the point is, for general interacting theory, we don't have box act on phi equals to 0. Okay? We don't have that. We have box act on phi equal to something. Okay? Something is highly non-trivial. That's the point. This means we have to calculate the right-hand side, in particular this term. You see, for interacting theory, this term becomes non-trivial, as we emphasize. When we check back to the free theory, this is trivial. Yeah? 0, then throw it away. But for interacting, this is not trivial. We have to do something there. That's the key. So second, consider theory. Consider interacting theory. For example, with the Lagrangian, including both free part, I use the L0. L0 means the standard free Lagrangian, okay? Standard free Lagrangian. And with also additional interacting part, which is as a function of phi, okay? Right, in general. Now the equation of motion will become the ordinary free part box plus m squared atom phi now minus the additional term which contributed by this interacting Lagrange. Okay. For example, now the new equation of motion is like this. Okay. Because now I restrict the interacting part. It's only a function of phi. Then when you derive equation of motion, you have to vary this phi and also vary this phi, right? So in this case, you will get to the new term, which is derivative for the with respect to phi. Okay. Then this will be the new equation of motion. Now it comes to the k. We're going to use this equation. Remember that this box x actually denoted to box plus m squared. Okay? I don't want to write too many. It's already very long. This box x. You can think about this box plus m squared. Sometimes I throw away my terms. You should, yeah, it's trivial. You should remember that. So now it comes to the key point. Key point is we're going to replace that. We're going to replace here by using the interacting equation of motion, interacting theory equation of motion, which means that this equation now it becomes equal to L interact partial. Okay. This equation of motion tells us this box phi equals to this one. Okay. Place it. I can place it. But if you're a serious person, you should crystal clear what you're doing. Okay. When you do this replacement, what are you actually doing? Okay. Because these objects are all inserted in some correlators. Okay. Okay. You're doing a replacement inside a correlation function. You're not doing some classic equation, A equals to B, then you can exchange. That will be okay, but here a little bit more attention. You're doing some operator replacement, okay? So all these things have to be viewed as operators, you see, because they are stay inside the correlation function, okay? You should be viewed as quantum operators. Now with this replacement, you have to be really careful. You actually assume the classic level equation of motion for interacting theory is still true as operator equation. Is that clear? Because at this moment here, it's just classic equation of motion. But when I do the replacement here, I assume that this is still true, even as operator. Even though you promote everything into operator, it is still true. Okay? Is that clear? So with that replacement, we really view this equation of motion as operator equation. Okay? Then we arrived at this is the K. So this is the equation is actually has a famous name, which is Schwinger-Dyson equation. This is the Schwinger-Dyson equation. This is the Schwinger-Dyson equation. Again, in order to compute the time-ordered correlators, we're going to use this Schwinger-Dyson equation. Okay. Yeah, maybe we should have a break. Let's have 10 minutes break.
等于这个 L 撇这个玩意就稍等垂线再加上眼圈等于头。
所以就是一周一个，这周不给了，下周给本。下周他们好交钱，然后我走到那个还有一些货，反正也。
所以互相尊重。那个同病很大。
那代表真不看，就是他就是说，它和自由的真空态不一样，发生自由，就这两个矢量不是相等。generally 一般是不一样的。比如说你是减的，你是一个 phi 3次的一个 interaction， 可能它显然是会，不是，就是你在经典情况下不是 phi 的一个零升。
这两条，这个也是 free。
不过你单纯的是一个 phi 次 interaction，
所以会有一个
它前面的蓝大互相
说它运行
互相作用是一样的，因为还是因为经典情况下能量最低还是 phi 0。
这里呢，如果你们尝试到大家都有一个区别实验的话，然后让你里面知道12点半协定，还是公会就是传教系
这个是它弱的时候这边的加一个点，然后这个鸡是这个是什么？
气就是气就是我说那个
还没教算这个。
就是你右引多少？
好，这就一来就是总重量数。哦，这个 P_I 是总重量。
我好像上全是10的。
我讲也是算。
一个是一个矩阵，那为什么？哦，
然后你想
64了解。
算那个稀释比例，这个就也可以通过算这个分解关联函数就可以知道它。
哦，哎，等一下，这个德尔塔加平方，这个是上节课推的那个。
有一种光层里面4个维。
对。哦，就要算这个。那最后就是算这个。
不是，就是你直接自己走边计算，然后你把这个这分解成4个你自己。这个就可以。这个分解关，
这个是有分解关系的，
是你有办法算。
前面那个 GV，
你把这个东西给完给做这 n 个看起来像互联网同时
好。
所以说接下来的问题是，
然后就是在算这个，
就是看怎么算相互作用。
这个上去，这个就是这个 T 是那个交换的意思吧？
就是我多理解。
不是，好像在
对。然后对，但这个还是不好。
他在算这个是 CPT。
这个那就是完全差不多就是弄跟现在
这课上完了吗？
要期去讲。这个你下吧。
然后下面是
做。
我今天要连上的。希望可以看。这什么？
这里会是讲一半，我这里也不知道。我刚刚还是讲的时候，刚刚开始算 无性流放就是是这样吗？就是说，你也知道，我也带去这个国家相处，但是可以怎么样？你说，不是那个过啥的问题。就
那我肯定会撞的嘛。
特别起来，
我身体大概有点像都有。
但是最近比如说这个三角
不是这样对情况来讲，
两个人是同步的，
其他的，其他的这个啊，讲点词哦，讲点词。
States 那那种我写写太长了，我是写特长，第一个的，第二个就是看我看，直接上去如果就不行不行，我就给他的可以选择的，跟他写了，我做那些这里是能出现，如果都是这个States 有一个人就从了，有一点没有。对，我所以一般就因为少有的人其实左右不同项目应该都有是，然后这个只要有课程就是变得神奇就是super way super way state 就是它局部的是然后是最厉害的学校最低的，然后就是探查这个这个是比如在体验自己，对，先我做很简单，还是没有说很难，因为说我们要其他项目做点，然后这是一个例子，就这里考虑一个大一会这个是在当时的上课这是一个三对角，这个三对角，并且它是有一些交替，这个 SSS 那个有。对，所以我现在还就承认。一次我带去那个时候就是打上这个奖，为什么不要基于要强有非常时间对，是一个城市，这个是这个时候是一个时间，第一它这个时间差不多啊，把第一个在对角就是对角化我们可以我们 PPT 或者说是分销这可能就是真的是这样比较好，在写一点这三个项，相当他们是比较大，是另外一个很上造成
这句话的翻译不要
是也
但是这个是这个
这个就是如果你直接用真空再去加400万，
这个哦，但这个是这个就是四维扩展的那个，
这些就是要不是有的，
但这个
对这个
哦，但是感觉这是一种上的，
对，但是只不过现在其他这个其他的也非常进到细啊，就相对于上不是说
就上会的话，那是有的话，
是这样子，其实是
下回再来下回可以。那还
真的是能不能这种，而有些的是，
不知道他们还有
有些时候
个人应该只有一点。
这个区域，它的话，可能叫做对对有效模式。理解正常的物体大小也可以，或者色散的它我加数字或者是好像是两个，你要真不找到就不来。
还好，作业游戏，你有啥作业？当时第一次看，自己不看。
我已经这样改了。
我这个腿上来会感觉是
因为我这个特别明显。
好的，有道理。没事，别人老板，他们可能会说，这个基本上都已经被取到，我单去了，
上课前广告给大家放一下，就今天这个课完了之后，6、7节，大概1点半开始，在教5、4、1、7，我会去接着上课，给另外一波学生上课，大概主题是讲科普内容，关于黑洞更高级一点的宇宙学。如果你们有时间有兴趣的话，欢迎你们去听。1点半在教5、4、1、7。Okay, so let's continue. We have to speed up a little bit to finish the content. So next step, we finished to derive the Schwinger-Dyson. Good. So next step, we're going to use this one to compute the parameters. That's what we're going to do. And again, we want to introduce some easy locations. We don't want to write too many samples. So easy notation. This is the first step. In order to do the systematic translation, introduce the notations. For example, from now on, we're going to simplify further the notations. We're going to just put the position at the index, okay? So phi x really means the phi operator at x, okay? And phi j really means the phi xj. Okay? Now, furthermore, delta xi now really means the delta, the four-dimensional delta function x minus x. Okay? It's a super easy notations. See? It's just notation. Okay? And d ij equals to dji will be defined as the df xi xj. Okay? ij equals to ji, right? Why? It's time order. Okay? We don't do time orders, possibly not. If after time order, it doesn't care. It's ij equals to ji. Okay? It's time order. Okay. And the switch the conditions. It's defined this way. Now, using these super easy notations, we can write the green function equation, for example, as the first exercise. So when we check the green function for the green function equation for D, then I can write that the box x d x1, right? I'm trying to get used to familiar with get used to my new notation. Okay, the right answer. So I should get box x d x1. Dx1 means d, right? Really means dx x1. Okay. See, this will be equal to minus I delta x1. Okay, very simple. See, super simplified. Green function. Green functions. Now we use all these new notations to try to calculate the thing we want. Okay. So what is the first object we're going to compute? Don't forget, the first object that we're going to compute is the 2-point function. Here, all the point function means time order function. 2-point time order function for the interacting theory. Remember that? That's still our problem. We didn't solve it. Okay, initial problem. So let's start from there. Consider this is our problem. Okay. Now using this super easy notation, the problem is this one. Yeah. This is my super simplified notation. You see, I want to compute this object. So what is this? I use some trick. Okay, I use some trick. The trick you should be familiar. First trick is I insert some dirt function. The dirt function by definition will here, combined with the integral will here. It will be here. Okay. This will be equal to this one. Can you check yourself? Okay. Just it should be equal, right?
Yes.
See? Because that's the definition of dirt function. If dirt function exists, then combined with the integral. The integral will kill the delta function. The payment is x has to be replaced by 1. Okay. Then it becomes phi 1, phi 2. No. This is by definition. Okay. This is true. Now, I'm trying to use this green function here. This green function here, the delta equals to box E. Okay. I can replace this delta by this left-hand side. No? Okay? It looks strange, but let's do it. It's true, right? It's true. So this will be equal to I integral box x e x1 with 5x by 2. Clear? Okay? Be okay, right? And by integration by part, again, I often use this one. By integration by part, this will be equals to e x1 fork x act on the later of equal to this one, right? Up to a total derivative, right? This total derivative with this integral is gone. I assume the boundary is trivial, okay? Then this will be equal to this one. again, now I didn't restrict, first of all, for this one, I didn't restrict it to myself to the free case, but you can check the free case, okay? Again, check. I get some equation, this equals this. Now let's check. So in free case, what happened? In free case, what happened? In free case, we have box. Now you might say, okay, in free case, they might be sorry. That's actually not true. Okay. In free case, box 5 is there. Doesn't mean box this one is there. Okay. In free case, this is actually the equation we just write somewhere. In free case, we got both x, phi y is actually minus the I delta xy, which is actually nothing but this equation, okay? Equation. Now you just plug into the last step. I just check the consistency. Because of this, I plug into here. I will get phi 1, phi 2 will be equal to the integral dx1. There's dx1, right? And there's a delta x2. Okay? I want to check my free case. The free case is this equals to this one. Okay? Now what is this? What is this? It's a third function. Now this is the integral over delta x. So this x has to be equals to 2, right? The integral here to third function. And replace the x by 2. Okay? Now this is d21 or d12. That's the same. So it's perfectly consistent with the original definition. We know in free case, this time order correlate is indeed d. Okay? D. Just to check. Once you develop some equations, you always can check the truth. Okay? Now let's do further check. Still in free case. What is that? Let's check for some 4 points. Okay. Even though you can follow the Wicked theorem for 4-point function immediately. Last time in the end we introduced Wicked theorem, so you can immediately write around the result. But let's use the trick here. We just developed to check consistency. What happened for 4 points? So in 4 points, you can do it step by step. The first one, you can, again, the lesson here is we can always write that kind of correlation function equals to this one. Okay, that's the lesson. Okay, we can replace the phi 1 by phi x. We can multiply a box x with addition of dx1. Okay, that's the lesson. So we can employ the final result for such kind of correlation in the same thing here. Okay, so you can view this as an improvement for your phi 1. Okay, you don't touch phi 2. The phi 2 is always there. Okay, but for phi 1, you can improve it in this way. Okay? That's the lesson. So with that knowledge for lesson, we can safely write these 4 points. The same thing. Okay. Without any trouble. You see, I did the same thing. You see, don't touch 2, 3, 4, but improve the phi 1. Okay, I get this. Is that clear? And again, following Schwinger-Dyson, now we get this one, right? Now we get this one. Now this is a box actor on some 4 points. Okay, so I should be able to employ Schwinger-Dyson. Where is my Schwinger-Dyson? Schwinger-Dyson is here. See, Schwinger-Dyson tells you when you face the problem how to calculate a box with multiple correlator with the bracket or with the time order scaling function, it should equal to this one, okay? It should equal to this one. It should equal to this. And I should be able to use this one, this Schwinger-Dyson, to go further. So what is this? We write it here. Using Schwinger-Dyson, you can easily check. Since the series is free, the first term in the right-hand side is trivial, okay? Because the box it was shifted inside, and the equation of motion here means left will be trivial, but you have many second terms. The second term is the sum, okay? Second term is the sum. Second term is the sum. Now you ask, what is the sum? What is the region of the sum? What is J? What is the domain of J? J runs from where to where? Okay, that's the question. So J runs from where to where? J runs from 1 to n, okay? J runs from 1 to n, you can see. Now in that case, J should run over 2, 3, 4, you see? Right? You have 3 terms. Only in Schwinger-Dyson, you have three terms. So using Schwinger-Dyson here, continue, this will be, let me write. Now what is that? Right-hand side there, Schwinger-Dyson tells you that just you obtain some dirt function and 2 points lower correlators. See? But now you have 3 sums because J run over 2, 3, 4. See, this is the result come from Schwinger-Dyson. Right? Delta with some 2 low point correlators, right? Right? I throw away this one because in free case this is true. Now I'm still checking the free case 4-point function result. So what is this? What is this? Now let's do the integral. Then this third function will be cleared and send this x to 2. Okay? So the first term, what I get is d1, 2. This is by definition d3, 4. Now plus second, this is the x3, okay? This is the x3. Now this x has to be sent to 3. So what I get is d1, 3. And with this is d4, 2. The same here. I should be able to get d1, 4. And with this d2, 3. Okay? Familiar with this result? This is perfectly consistent with the weak theorem's result. Okay? Nothing but the weak theorem's result. Okay? Now these are the trivial exercise. Trivial exercise. You want to get familiar with this trick. Okay? Trick is to insert delta function, replace the delta function by the box D, something like that. Now let's go to non-trivial case. We turn on interaction. Turn on interaction means turn on the LIT. Okay? The interaction form. Now let's focus on this case. This interaction phi will be the phi-cubic couple. The cubic couple. Focus on this case. Let's fix this so-called phi-cubic theory. Phi-cubic theory. In this case, think about, as emphasized before, this equation is called equation number 1. This equation is generally true for interacting. It's generally true. Generally. Doesn't care or interacting, right? Because we derive the result and assume this is free, generally true. Let's start from here. Because we want to, our initial problem, compute this guy for the interacting case. Now, equation 1 becomes phi 1, phi 2, 2 points will be equals to I integral d1x. There's a d1x, right? Now the key point is, in the interacting case, how to deal with this term. You see? So we have to use the general Schwinger-Dyson to replace the box, okay? To calculate the box. It's not free anymore. Now it's interacting. Now, when it's interacting, we have to use this general right-hand side. There should be 2 terms. See? One term is the box by inside, another term is the term. You see? So with that in mind, what I should obtain there is the L entire. Take a derivative with phi, okay? Then you will get something like to make it clear, conclusion, notation clear. Let's use G instead of lambda. So in this case, the partial L, partial phi will be equal to G over 2 phi squared. See? G over 2 phi squared. Now I should plug in G over 2 here. Right? Right? Because I should plug in this G over 2 phi squared here. Right? To replace the box phi. Okay? Then the result I obtain is G over 2 phi x squared. See? I already replaced using the equation motion for the interacting series. Okay. And don't forget that there is a third function piece. There's a minus I delta x2. Okay. This will be the first step really working in this interacting series setting. Okay. This will be the first. Now let me continue. So what is this? Oh, this term is super easy since I already get a single delta from trying. I should be able to compute this integral for the second. So the second contributor is D12, right? By definition, you see it? See it? The important thing you should be able to pay attention is this D, even though working in this interacting series, this D is near the free Feynman propagator. Okay? Is that okay? You have to pay attention. Don't confuse yourself. Don't confuse yourself. Why? Why? Because we use the mathematical identity to replace delta function. Okay? Using this box D, okay? This is mathematically true, okay? Doesn't matter you do this replacement for the interacting series or free series. This is mathematically true. So I insert this D, even though it's a free propagator. Now somehow to represent my interacting series result support function. This is mathematically no problem. Can do that. This is the reason why we could be able to obtain a term D12, even though for interacting. Of course, I have some more terms, which indicate this is the interacting series. It's not only a single phrase. So what about this term? This term looks a little more weird. So this term is the G over 2 dx d. Now, since I said this trick can be used to improve the phi 1, okay? Okay? Then think about a few seconds. Nobody forbid you to using this improvement trick also for phi 2. Okay? See? Just a simple trick. You see? I can choose to improve phi 2. No problem. Which means here, for this correlator, I can further use the same trick now for phi 2. Okay? Okay? You might think this is crazy, but it's useful. You will see. So if I improve for phi 2, I build up one more integral, but now for y variable. Okay? Y variable, in order to distinguish from the class. Now, as you can see, I just use the same trick. Then I should be able to get one more dy2. Okay? Because now I improve phi 2 using the same trick. Now what I obtained is, now we have a box y. Okay? We have a box y. Y. And act on what? Act on phi x squared by y. Because the trick led me to improve phi 2, then phi 2 disappeared. We have the phi y left. Okay? Just use the same trick. Now use the same trick, so what? So again, we are faced to calculate something like a box act on some correlators for interacting case. Don't forget, okay? Okay? Is that clear? Then we can use again the Schwinger-Dyson, right? Whenever you see this, you should use Schwinger-Dyson. You see? So use Schwinger-Dyson, what do you get? You see it? So you repeatedly to use Schwinger-Dyson. Now what you get is this will be equals to d12 minus there's once more g over 2. Okay, right? You use Schwinger-Dyson again. So then there's a g squared over 4. dx1 d2y phi x phi 1. Okay, you see? Because now you are going to use Schwinger-Dyson for y position. Now you should be able to get a phi y squared. Okay? That's coming from the right hand side. Okay? Right hand side. So at this step, you just forget about phi x. You fix phi x. Or you try to employ Schwinger-Dyson for box y phi y. Okay? Then you get this term. And of course, not only that, but one more term. Right? One more term. One more term. Yeah, you can check yourself. It looks a little bit involved, but you can check yourself. This is a straightforward. You just repeatedly use both the trick and the Schwinger-Dyson result. That's enough. That's the only thing we need to. We don't need anything else. We can achieve this. That clear? Yeah, up to here, do you have any question? Now we come to the key point. Now you see the magic. Now you see the magic. The magic now comes. It seems we start from some very simple object. But the point is this object is for interacting theory. Okay? You shouldn't view this is really simple, okay? This is a measure a 2-point correlator, but in interacting theory. Since the theory is interacting, which means a field can become two fields, okay? Because there's a 5-qubit interaction there, okay? The operators can change to some others, okay? That makes the problem really not simple. Now I use some little weird trick and repeatedly use some tricks. Eventually I arrived at this term. But when you arrive at this term, you should think about it. Then this result is nice in a sense that, look, I have a G squared coupling here. G, remember G is the parameter measure the coupling for the interaction, okay? Okay? So if the coupling G is small, I can replace this correlator, even though this correlator at this step is still the interacting bracket, okay? But I can approximate this bracket by free theory. Why? Because G is small. If G is small, if I only care about the result up to G square order, then I can replace this one by free result. Clear? Because there's a small coupling. You can expand your result in terms of this small parameter. You should be able to get order by order, okay? Right? The first order maybe is independent of G. Maybe the second order is G linear. Maybe the next order is G square and G qubit, blah, 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 things like that. But the point is now I already separated out a G square in front, okay? If you insist this object is still depend on G, maybe it's linear depend on G or G square, then this total result is just the lower order, okay? Which I don't want, okay? I don't care because G is so small. I don't care the many, many higher and further orders. I only care up to G square order. Then you can safely calculate this one or replace this one by free result, free theory. That's logic, okay? So we use trick to translate my interacting correlators to some structure. That some structure factorizes out the coupling, okay? And then I replace the remaining object by the free result. Then I get the so-called perturbative result for my interacting correlator. Okay, that's logic. Do you have any question about this logic? How we deal with this one? This is so-called a perturbative way. Okay, perturbative way. Perturbative means perturbative is 围绕。OK， perturbative means 如果我的 theory 有一个小的参数，那我就 always 可以对这个小参数做展开，一级一级的计算。如果我只关心 up to 平方阶，那我看到这样的结果，我直接可以用自由场景去替换它。
为什么我们一次性是开到2阶上，而不是就只保留线形象？
There's no linear, as you say.
我说后面还有个 IG 吗
No, we're going to continue to compute this one. G squared, same order. Okay. Now there's one remaining term. We're going to continue to compute. So this term seems we already solved because there already is the G squared. What about this? The last term. So for the last term, we will continue to employ the trick. As you should be now familiar, the trick, let this last term become this one. Okay? I improve the x by a new variable y. Then I get a d times the box x on y. Okay? This is the third function insertion trick. Result. Now what is this? Again, you use Schwinger-Dyson. Okay? You use Schwinger-Dyson. That's always the then you get a g over 2, additional g over 2, because you use the Schwinger-Dyson. Okay? Now you get dxy and 5y squared. Okay? You get this one. Okay? Because this is a single insertion, you will not have a very function piece. You just only have Schwinger-Dyson right hand side. Okay? The coupling term will be equal to this one. And what is this? You see, now up to here, I have one more g separated out. Together with this g, they become the same order. So if that g squared separated out, the leftover thing I can again approximate by free theorem. See? So using that logic, I can approximate this one or take this value using free result. This will be the dxy d. Remember that this is nothing but dyy, okay? dyy. dyy is just a propagator back itself, okay? The same insertion. dyy. There are higher terms, right? The higher terms, I don't want to care. Because this g squared compared with g, it becomes g cubic. The higher terms. I threw it away. Okay. Now I can package some, like I can wrap up my result because I essentially finished all the calculation. Finished everything. Now I can wrap. Now take care of all these terms. Take care of all these terms. And take care of all these terms. And don't forget that here is the highly non-trivial, even though you can approximate it by free theory. But this is the highly non-trivial 4-point function, okay? So, but we know how to calculate this one using either Wick's theorem or the result here. We know basically everything. Now you should wrap up the result, the whole result. Put everything together. Put everything together. Put everything together, we eventually get the final result for the interaction 2-point project. Then we obtain phi 1, phi 2, 2-point equal to d12, right? The first term is d12. Where's my d12? D12 is here. Okay. d12. Now next term is g squared dx dy half d1x dxy dy2 plus order d1x dxx dyy dy2 plus half d1x d2x dxy dyy. Okay. Can you check it straightforwardly? Everything following there, right? Following there. See? See? There are different contractions for these 4 points. Okay? There are different contractions in these 4 points. It's basically 3 terms. Okay? 3 terms. Now, since there's only x, x, y, y, 3 terms become 2 independent terms. Okay? And together with this d1x, dy2, it becomes this 3 terms. It becomes this 3 terms. That clear? Here I use the put more details. I use for this equation, I use phi x, phi y, y, phi y, phi y. These are 4 points. Essentially, over there, in the free case, this should be the dx, x, dy, y, or approximate class. And the 2 twice dxy squared plus higher order. Higher order I throw it away. Okay? So I use this basically free result to approximate these points, these 4 points. Okay? These 4 points. Then you plug in together with this, with this. You get this one, this 2, plus the last one. Okay? And you can check, then these 3 pieces share the same order. The order in terms of the small parameter coupling. Okay? Then I put them together. This is my final result. Now, if you're a curious person, you don't like this algebraic polynomial or term, you can immediately observe that there is a graph representation for this result, right? You can make a graph. There's some rule behind. Look, okay? Make a graph. Why not? Okay? I often did this, right? Because when I was asked to remember something, usually I cannot. I can only remember the graph, so I translate everything to graph. Then there's a graph structure behind this result. So what is that graph? Can you try to write this draw graph? The first term, which graph can represent the first term? The first D1, 2. Okay, let's use this. Of course, this will mean 1 and 2. Okay, D1, 2 means propagator between 1 and 2. Okay, I use this. What about the next? Because this is the plus. Okay, these terms add up together. So what about the second? What about the second term? The second term, there is d1x, which means I should start from 1. Okay, I should end up at some point x. Okay, is that clear? Because all these 1, x, 2, or y are the positions. Okay, you should view it as the position in space-time. Okay, then when you make the graph, you should do it this way. Now what else? Following this d1x, there are 2 dxy. Okay, each d means propagator, right? Propagator from this position to other position, which means there are 2 propagators attached at the x position. You see? You see? So out of this x, there should be 2 lines outcome. Okay, 2 lines outcome. Both of them permanent as another position, which is y. You see? Now it's not finished yet. It's still followed by a dy2. So you should continue to develop from y and end up at some point 2. You see? So I just stupidly using graph to represent my math result. No more than that. Then you just continue to work out this sum. For this graph, you see, I start from 1 and 2x. Okay? Now there's dxx. That's a little weird. It means you start from x and end up with x. What does that mean? But we know dxx is still non-trivial. So you should write something like this. Okay? Right? Reasonably. Now, there's dyy and dy2 is in the symmetry to this one. You see? So there's a similar structure for the y, and then end up at 2. Okay? So this is the third term. So last one, I start from 1 to x. I start from 1 to x. Now x to 2. Okay, I said 2x, x2 are the same. Okay, so this x is just continue to 2. Okay, but it's not finished. There's one more structure, x to y and y to y. So x has to be start from x, shoot from x, and then end up by y. Okay. Now again, there is a y back to itself. So which means there should be something like this. And I finish. So these are all the graphs. So if you have these graphs, wow, looks a little nicer, right? Much nicer. Than the algebraic formula. Okay. Then up to here, you're almost done. Okay. You realize that. Okay. Then if you are a lazy person like me, so you can forget about all the intermediate steps because you get the finalized rules. Okay. You have a graph rules for your problem. Then you can try to extract some general rules. General rules perhaps can let you just immediately write down the final result without any calculation. Okay? Without any calculation. So that's something called the Feynman rules. Because Feynman is a smart person, right? He's thinking that way. So laying out by hand. So this is the so-called Feynman rules. So let's try to write down the Feynman rules. Well, since this is important, let's a little bit of step by step. So start with points. xi, for which correlation function is measured. Draw a line from each point. Just like what I did. I just using words to summarize what I just did, okay, in drawing these graphs. Draw a line from each point. Such line can either contract to an existing line, or in this case, given a Feynman propagator, or you can split according to the interaction. This means what? This means why you are talking about such kind of splitting. You see, here means splitting, right? Splitting means from a single line it becomes two. Okay, split, okay, split. So why such kind of splitting? Not something else. This was completely determined by the interacting theory. Since from the interacting theory here, we are focused on some theory. Where's my theory? Here. Since in my interacting theory, we are focusing on there are 3 phi. Okay, see. So the splitting following this rule. Since I have 3 phi operators, which means there could be a vortex has 3 lines meet together. Okay, very intuitive, right? Right? Because there's a coupling. There are 3 phis, means 3 lines can meet together. Okay, this determines my stability. And each splitting, since it comes is essentially originally come from here, so each splitting will contribute a factor. Which factor? Factor comes from here, right? Factor comes from here. Factor comes from here. That factor comes from here. Which means if you are a lazy person, you don't want the intermediate steps. You just want to go to the final result. Now, after you finish to drawing this graph, how to assign the mathematical structure to these graphs? In that case, whenever you have that kind of splitting point, you have to put a coupling. You have to put a coupling here. For example, here I put a G, one more G. Here G, G, here G. G. Okay? Reasonably, right? Because this splitting comes from there. So there's a coupling parameter there. So for each splitting, you have multiply this G. Okay. Multiply this G. So each vertex, we call that kind of thing vertex. So each vertex contributes a coupling. And last, we have to sum over all diagrams, all graphs, with all lines. With all lines contracted. Okay? Means what? Means you shouldn't, when you draw this graph, you shouldn't, you start from some external point, y, okay? Then you starting to move into, draw into inside. You shouldn't let some point just terminate and end up here. No, stop somewhere. You shouldn't do that, okay? All the internal positions has to be contracted over. Okay? You either split or you close, or you contract with some other lines. Okay, you cannot just stop inside. Okay, no, that's the rule. This is the rule. Then the rule is very simple. The rule is very simple. The point is you should find all the possible such graphs following these rules. Okay, you can check yourself for 2 points for the bicubic interaction. These are all the graphs. Okay, no more than that. Okay, this is the only graph you can draw. Okay, then you sum over all this. Okay, sum over all this means for this part you sum over together. But if this is a single graph, you have 2 disconnected pieces. For example, sometimes you should multiply them. Okay, you should multiply, and then for these different graphs, you should sum over this. Okay, that basically the whole story. One final remarks, which is also very, very important. If you are a careful person, then you immediately realize this rule does not care these factors. Right? Does not explain these factors. Why I should put a half here, a quarter here, and a half again here. The rule doesn't care much about this one, right? Doesn't care about details about this one. So this is the final remarks. The final remarks is, when I add these coupling parameters, I essentially throw away this 3 factorial. Okay, you see? Then you might ask me, why don't you put this whole thing together, right? You can view this whole thing as a coupling. Yes, it's true. But the point is, a careful examination tells that you can throw away these 3 factorials. Okay, throw away these 3 factorials. And above on that, you should divide by something called the symmetry function. divided by symmetry factor. So what is symmetry factor? For example, this is 2, this is 4, this is 2. How do I know this is 2, 4, 2? Because in this figure, if you flip this upper line and this lower line, okay, you get the symmetry. If flip it, the graph does not change, okay? The same graph. It indicates there's some overcounting. Okay? You should divide it by the factor. For this also, if I switch these two splitting outcome lines, these two, then the graph does not change. And for this one also does not change. So the symmetry factor for this graph is 2 by 2. It's 4. Okay. The symmetry factor for this one is again, if I switch these two splitting outcome from this vertex, the graph does not change. So you overcounting by 2. So the symmetry factors for these three graphs are 2, 4, 2. That's why I divided 2, 4, 2. That's it. Okay. Of course, if you believe me, just accept whatever I said. But if you can check yourself, it's not super difficult. It's very easy to check. You can check it. You can check it. Okay. So continue to be the task today. So do you have any questions? Maybe one last question.
那它那个负号是怎么来的？就为什么是负 GP 吗？不是正 GP？
Which is minus sign?
就是
Good. That's right. So the rules, I say that coupling here, coupling is actually minus IG. So whenever I mean I multiply a coupling parameter, I mean IG. Now if you have two IG, you get minus sign. If you have 3, you get 2. Any other question? Any other question? You might continue to ask, say, it seems a little artificial. Why? I said that this should multiply IT, not minus T or plus T or 2G or something. The point is, this is no more than some rules, okay? I calculate the result from principles. That's well defined, unique, okay? I don't need the graph in principle to calculate the result for sure. Now I'm telling you that there's an easy graph rule, okay? Then in order to build up these rules, you just compare with the explicit result, translate it into graph rules. After I know these graph rules, I think it skips the calculation details. Okay? I don't need to calculate it. Hand me a theory, I just follow the Feynman rule and write down the final result.
这个你在考虑对称性的时候，除了旋转，还能有其他的对称性，比如对线和线之间可以交换之类的。
考虑的对称性是线和线的交换。
对，就是从一个零点出来的两个 splitting， 如果它们不能分辨，那这个图来看，交换它们不能分辨，就 indicate 你有 overcome。
这种。
Well, again, it's not something mysterious. Okay, let me put it one more thing. Here, I have to emphasize all internal lines integrated over internal points integrated over. Because we integrated over x, y. X, y we call the internal points. All the internal points integrated over. Now, about the symmetry factor, let me tell you how to derive it explicitly. It's very easy. Now, this symmetry factor comes from where? If you think about it carefully, this kind of contraction, okay? We call it sometimes contraction, right? If you think about it carefully, for this graph, for example, how many operators do you have? Let me try to write everything explicitly. There's a phi 1 here, okay? Okay? There's 3 phi x here. Let's use algebraic contraction to understand the symmetry factor, okay? Now there are 3 phi 1, right? Otherwise, the contraction is not well defined, right? Because at the same point that you contract it with 3 other points, which means there are 3 operators. Now there's a phi 2. So this is the entire, little complicated, but this is the entire object prepared for the contraction, for the possible contraction, right? Now you learn how to contract in your free theory, right? It's not no more than that.